and then you keep on applying the resolution rules, and you return entailment if you can derive false. Okay, so here's an example of what this looks like. So here's a knowledge base, and here's a particular formula, and I want to know whether KB entails F or not. Okay, so you add it, add not F into the knowledge base, so that's not C. And I'm going to convert this into a CNF, so that only affects the first formula here. And then I'm going to repeatedly apply the resolution rule. So I can take this clause. Resolution allows me to cancel not A with A. I get B or C. And then I take B and not B, cancel it out. C, and I cancel out C. I mean, when you see C and not C, that's clearly a contradiction, and you can derive false. Which means that the knowledge base entails F in this particular example. Okay. This also maybe gives a little bit of intuition of the mysteries of defining the goal clause and horn clauses as deriving of, blah, blah, blah implies false. Because you can add something that you're trying to prove, and you can use modus ponens to see if you can derive false. And if you do derive false, then it's a contradiction. All right, so as I alluded to before, there's a time complexity difference between modus ponens and resolution. So for modus ponens, each rule application adds a clause with one propositional symbol. So imagine you have n propositional symbols. You can really only apply modus ponens n times. So that's linear number of applications there. Whereas the thing with resolution is that you can add, each rule application can add a clause with many propositional symbols. And in the worst case, you can imagine any subset of the propositional symbols getting added, and this results in an exponential time algorithm. This should not be surprising because we know that 3-SAT is NP complete. So unless there was some magic here, there's no way to kind of circumvent that. Yeah?
So why is resolution then, and maybe I'm wrong on this, but why is it preferred?
So the question is, why is resolution preferred? So you could just convert everything to CNF and check, do backtracking search or whatever on CNF. Resolution turns out that it will have generalizations to first order logic, which model checking doesn't. Right. So remember, there's two ways you can go about. You can basically reduce things to CSPs, and then you can solve it, or you can try to use inference rules. So this inference rule doesn't, as far as I know, people don't really use resolution in propositional logic, but in first order logic, you kind of have no choice.
Could you distill, though, like, I'm thinking that when you see the modus ponens inference rule, it's kind of like everything's getting distilled down to and relationships.
Yeah.
Like sort of NAND and NOR are the universal gates. And so I'm thinking that resolution is like a NOR reduction and modus ponens is a NAND reduction. So aren't the two, couldn't you convert from one to the other?
The question is whether the two are, resolution looks like kind of like NAND. There's quite a bit of difference there. Maybe we could talk about it offline. Yeah. Okay, so summarize, there's two routes here. You can say, I'm going to use propositional logic with horn clauses and be using modus ponens. This is fast, but it's less expressive. Or I can embrace the full complexity of a propositional logic and use resolution. And this is exponential time. It's slow, but it's more expressive. Yeah?
So by less expressive, you mean it takes more symbols to represent the same truth formula? Or there are things that can't be expressed in horn clauses that can be expressed in propositional logic?
Right. What do I mean by expressive? I mean the latter, which is that there's simply some things you can't write down with using horn clauses. Like you can't write down rain or snow at all. Any sort of branching or disjunction you can't do in horn clauses. So in some applications, horn clauses actually turns out to be quite enough. So these type of horn clauses show up in programming languages where you're just, you see some premises and you're trying to derive some other quantities. So like in program analysis, this is actually quite useful and efficient. Okay, so let's move to first-order logic. So what's wrong with propositional logic? I mean, it's already exponential time, so it better be pretty good. So remember, the point of logic is to, in general, from an AI perspective, is to be able to represent and reason with knowledge in the world. So there's a lot of things that we want to represent, but might be awkward in propositional logic. So here's an example. So Alice and Bob both know arithmetic. So how would you do this in propositional logic? Well, propositional logic is about propositions. So this has two propositions, which are statements, which are either true or false. Alice knows arithmetic and Bob knows arithmetic. Okay, fine. So what about all students know arithmetic? How would you represent that? Well, you probably do something like this, where you say, okay, if Alice is a student, then Alice knows arithmetic. If Bob is a student, Bob knows arithmetic, and so on. Because all propositional logic can do is reason about statements. So what about this? This is Goldbach's conjecture. Every even integer greater than 2 is the sum of 2 primes. So good luck with that. You might have to write down all the integers, which there are a lot of them. So propositional logic is clunky at best and not expressive in the worst. What's missing? When we have knowledge in the world, it's often more natural to think about there as being objects and predicates on these objects rather than just opaque propositions. So Alice knows arithmetic actually has more internal structure. It's not just a single proposition that has nothing to do with anything else. It has notions of Alice and knows and arithmetic in it. And finally, once you can decompose a proposition into parts, you can do fancy things with them. You can use quantifiers and variables. For example, all is a quantifier that applies to each person, and we want to do that inference without enumerating over all the people or all the integers. Okay, so I'm going to talk about first-order logic, going through our plan of first talking about the syntax, then the semantics, and then inference rules. So I want to warm up with just some examples. I'm not going to do as rigorous of a treatment of first-order logic as propositional logic because it gets more complicated, and I just want to give you an idea of how it works. So Alice and Bob both know arithmetic. This is going to be represented as knows Alice arithmetic and knows Bob arithmetic. Okay, so this is there are some familiar symbols like and now the propositional symbols have been replaced with these more structured objects. And all students who know arithmetic gets mapped to this, where now I have this quantifier for all x. Student of x implies knows x arithmetic. Okay, so a bit more formally, so there's a bunch of definitions I'm going to talk about. So first-order logic. So in first-order logic, there's two types of things. There's terms, and then there's formulas. In propositional logic, there are only formulas. So terms are expressions that refer to objects. So it could be a constant symbol. It could be a variable, or it could be a function applied to some other terms. So for example, arithmetic is just a constant. Think about it as a name. There are variables like x, which I'll explain later, and there's function of terms. So 3 plus x would be represented as sum of 3 and x. Okay, remember, these are just symbols. And formulas refer to truth values. So there's atomic formulas or atoms. So this atomic formula is a predicate applied to terms. So knows, x is a term, arithmetic is a term, therefore a knows is a predicate. So knows x arithmetic is an atomic formula. So atoms are supposed to be indivisible, but here there's a substructure here, so maybe you can think about these as subatomic particles if that is useful. There's connectives as before. So what we're doing right now is you're taking these atomic formulas, atoms, and they behave like propositional symbols. So given these atoms are generalizations of propositional symbols, we can string them together using any number of connectives, as we've done in propositional logic. And then finally, we have quantifiers applied to formulas, which means that if you have a formula with a variable in it, we can stick a quantifier over these variables to specify how the variable is meant to be interpreted. Okay, so connectives and quantifiers. All right, so let's talk about quantifiers. Quantifiers are, in some sense, the heart of why first-order logic is useful. There's two types of quantifiers: universal quantifiers and existential quantifiers. So universal quantifiers you should think about as just glorified conjunction. So when I have for all x, p of x, that's really like saying p of a and p of b and p of c and for all the constant symbols. And existential quantifiers like glorified disjunction. When I say there exists x such that p of x holds, that's like saying p of a or p of b or and so on and so on. So I'm cheating a little bit because I'm still talking about the syntax of first order logic, but I can't resist but give you a little bit of intuition about what the syntax means. I'm not formally defining the interpretation function here, but I'm just trying to give you an idea of what the symbols correspond to. So here's some properties. So if I push a negation through a universal quantification, then that goes on the inside, and the for all becomes an exists. Does this sound familiar to people? What is the name for this kind of thing? Yeah, it's just De Morgan's law, but applied to first-order logic as opposed to propositional logic. And it's really important to remember that the order of quantifiers matters. Right? So for all exists is very different from exists for all. Okay, so one more comment about quantifiers. It will be useful to be able to convert natural language sentences into first-order logic. And on the assignment, you're going to do a bunch of this. But so this is kind of there's an important distinction I want to make. So in natural language, you have quantifiers in natural language are words like every or some or a. And so how do these get represented in formal logic? Every student knows arithmetic. Every generally refers to for all. So you might write something like this. But this is wrong. So what's wrong about this?
Not every x.
Sorry, say again?
Not every x. If you find an x that's not a student.
Yeah. So the problem is that, what does this say? This says everyone's a student. For all x, x is a student. And for all x, x knows arithmetic. So it's basically saying everyone's a student and everyone knows arithmetic, which is different. So what it really should be is implication. So for anyone that's not a student, I don't care in terms of this assessing the validity of this formula. And only if someone's a student, then I'm going to check whether that student knows arithmetic. Okay, so what about existential quantification? Some student knows arithmetic. This is student of x and knows x arithmetic. So notice the different connectives. And a general rule of thumb is that whenever you have universal quantification, it should be implication. And whenever you have existential quantification, it should be an and. So of course there is exceptions, but this is a general rule. Okay, so let me give you a few examples just to get you used to thinking about quantifiers. So imagine you want to say there is some course that every student has taken. So how is that? So there is some course, so there should be an exist y is a course that every student has taken. So every is for all x, and here I want student implies takes xy. Okay, remember exist usually has and for all has implies. Okay, what about Goldbach's conjecture? Every integer is greater than 2 is sum of two primes. This is every even integer. So every even integer greater than 2 implies that what about these? Is a sum of two primes. So notice that there are no maybe explicit hints that you need to use existential, but the fact that these two primes are kind of underspecified means that it should be exist. So there exists y and z such that both of them are prime, and the sum of y and z is x. And finally, here's a statement. If a student takes a course and the course covers a concept, then the student knows that concept. Whether that's true or not is a different matter, but this is a valid formula, and it can be represented as follows. So one other piece of advice is that if you see word if, that generally suggests that there's a bunch of universal quantifications. Because if is kind of like saying there's a general rule, and universal quantification says like in general something happens. So this is for all x, all y, all z. If you have a student and takes some course, and that course covers some concept z, then that student knows that concept. I guess technically there should be also and concept of z in there, but it's getting complicated. Okay. Any questions about first order logic, what the syntax is, and any of these intuitions that we're having for it? Yeah.
Just for clarification, is there any reason why you don't use the equal sign instead of just equals, or is that just to define a predicate equals?
So the question is, why don't we just use the equal sign? So I'm being a little bit, I guess, cautious in following the strict syntax where you have functions that just take it shows you the structure of the logical expressions more. So now in certain cases you can use syntactic sugar and you can write equals if you want. But remember, the point of logic is not to be able to write these things down manually and reason with them, but to have a very kind of primitively built system of formulas that you have general rules like resolution that can operate on them. Okay, so let's talk about the semantics of first order logic. So in propositional logic, a model was something that maps propositional symbols to truth values. In other words, it's a complete assignment of truth values to propositional symbols. So what is this in first order logic? So still, we're going to maintain the intuition that a model is supposed to represent a possible situation in the world. So I'm going to give you a graphical intuition. So imagine you only have unary and binary predicates. So these are predicates that only take one or two arguments. Then we can think about a model as being represented as a graph. So imagine you have 3 nodes. These represent the objects in the world. So objects are kind of first-class citizens in first-order logic. And these are labeled with constant symbols. So you have Alice, you have Bob and Robert, and you have arithmetic here. And then the directed edges are going to represent binary predicates. And these are going to be labeled with the predicate symbols. So here I have a nose predicate that applies to 0103, another nose predicate that applies to 0203, and a unary predicate here that applies to only 01. Okay? So more formally, a model in first-order logic is a mapping that takes every constant symbol to an object. So Alice goes to O1, Bob goes to O2, arithmetic goes to O3, and it maps predicate symbols to tuples of objects. So knows is a set of pairs such that the first element of the pair knows the second element of the pair. I'm skipping function symbols just for simplicity, but you would define them analogously as well. Okay, so that is a model. It's a little bit more complicated than propositional logic because you have to define something for both the constant symbols and the predicate symbols. So now, to make our lives a little bit easier, I'm going to introduce a restriction on a model. And it's motivated by the following example. So if I say John and Bob are students, then in your head you might imagine, well, there's two people, John and Bob, and they're both students. But there could be technically only one person whose name is both John and Bob, or someone who's anonymous and doesn't have a name. And there's two simplifications that rule out W2 and W3. So the unique names assumption says that each object has at most one constant symbol. And domain closure says that each symbol has at least one constant symbol. So the point of this restriction means that constant symbols and objects are in one-to-one relationship. And once you do that, then we can do something called propositionalization. And in this case, first-order logic is actually just a syntactic sugar for propositional logic. So if you have this knowledge base in first-order logic, student of Alice and student of Bob, for all students are people, and there's some creative student, then you can actually convert very simply into propositional logic by kind of unrolling. It's like unrolling your loops in some sense. So we just have student Alice implies person Alice, student Bob implies person Bob. And because there's a finite set of constant symbols, it's not going to be like an infinite set of formulas. There might be a lot of formulas, but it's not going to be an infinite set. Okay? So the point of doing this is now you can use any inference algorithm for propositional logic for first-order logic. Okay? So if you're willing to make this restriction, unique names and domain closure, that means you kind of have direct access to all the objects in the world via your constant symbols, in which case you're just propositional. You just have propositional logic. Okay, so why might you want to do this? So first-order logic as a syntactic sugar still might be convenient. You might still want to write down your expressions in first-order logic and have the benefits of actually having propositional logic where the inference is in some sense much more developed. But later we'll see that there's some cases where you won't be able to do this. Okay, so that's all I'm going to say about the semantics of first-order logic. So now let's talk about inference rules. Okay, so I'm going to start by talking about first-order logic with horn clauses. And we're going to use some generalization of modus ponens. And then we're going to move to full-on first-order logic and talk about the generalization of resolution. Okay, so let's begin by defining definite clauses for first-order logic. So remember, a definite clause in propositional logic was a conjunction of propositional symbols implies some other propositional symbol. And now the propositional symbols are now these atoms, atomic formulas. And furthermore, we might have variables, so we're going to have universal quantifiers on the outside. So intuitively, you should think about this as a single template that gets real. If you were to propositionalize, it would be a whole set of definite formulas in propositional logic. So another way to think about this is that this single statement is a very compact way of writing down what would be very kind of cumbersome in propositional logic, because you would have to instantiate all the possible symbols. Okay, so here's a formal definition. So a definite clause has the following form. You start by having a set of variables which are all universally quantified, and then you have atomic formulas which are all conjoined. It implies another atomic formula, and these atomic formulas can contain any of these variables. Okay, so now let's do modus ponens. So here's a straightforward generalization of modus ponens. You have some atomic formulas A1 through AK that you pick up, and then you have A1 through AK implies B, and then you use that to derive B. Okay, so it says the first attempt, so you might catch on the fact that this actually won't work. So why doesn't it work? So imagine you have P of Alice, and then you have for all x, P of x implies Q of x. So the problem is that you can't actually infer Q of Alice at all, because P of x here and P of Alice just don't match, right? This is supposed to be A1, this is supposed to be A1, and P of x and P of Alice are not the same A1. So this is kind of an important lesson, because remember, these inference rules don't know anything. They have no kind of intrinsic semantics. They're just pattern matching, right? So if you don't write your patterns right, then it's just not going to work. But we can fix this. And the solution involves two ideas, substitution and unification. So substitution is taking a formula, applying find and replace to generate another formula. So if I want to replace x with Alice, apply to P of x, I get P of Alice. I can do two find and replaces, x with Alice, y with z, and I'm going to replace x with Alice and y with z. And so in general, a substitution theta is some mapping from variables to terms. And substitution theta of f returns the result of just performing that substitution on f. So it generates another formula with these variables replaced with these terms. So pretty simple idea. Okay, unification takes two formulas and tries to make them the same. And to make them the same, you have to do some substitution, so it returns what substitution it needed to do that. Okay, so here's an example. Knows Alice arithmetic, knows x arithmetic. These expressions are not syntactically identical, but if I replace x with Alice, then they are identical. So that's what unification does. So what about this example? How do I make these two identical? I replace x with Alice and y with z. And what about this one? I can't do anything because I can only, remember, substitution only can replace variables with other things. It can't replace constant symbols. So I can't replace Alice with Bob. So that just fails. And then things can get a little bit more complicated when you have functional symbols. So here, to make these the same, I need to replace x with Alice, and then y with f of x, but x has already been replaced with Alice, so I need to make this y goes to f of Alice. Okay, so to summarize, the unification takes two formulas, f and g, and returns a substitution, which maps variables to terms. And this is the most general unifier, which means that if I unify x and x, I could also replace x with Alice, and that would be fine, but that's not the most general thing. I want to substitute as a little as possible to make two things equal. So unify returns a substitution such that, and here's an important property, if I apply that substitution to f, I get identically the same expression as if I apply theta to g. And if I can't do it, then I just fail. Okay, so now, yeah, question?
can we say that f of x, like what should we say to f of x? Is it a variable or is it a formula?
So the question is f of x, is this a variable or a formula? So f of x, f is a function symbol, so it takes a term and returns a term. So the technical term f of x is a term, which represents an object in the world. And you can check that nose is a predicate, so it needs to take terms. So f of x is a term. Okay, so now with substitution and unification, we can now revise our modus ponens to make it work. So I'm going to have a1 prime through ak prime, which are distinct syntactically from a1 through ak. And what I'm going to do is try to unify the primes and the not primes into some substitution. And once I have the substitution, I can apply this to b and derive b prime, and that's what I'm going to write down. Okay? So let me go through this example now. So suppose Alice has taken 221, and 221 covers MDPs. And I have this general rule that says if a student takes a course and the course covers topics, then that student knows that topic. So I need to unify this takes Alice 221, covers 221 MDP with this abstract version. And when I unify, I get the substitution to be x needs to be replaced with Alice, y with 221, and z with MDP. And then I can derive, and then I take this theta and I apply that substitution to nose xz, and I get nose Alice MDP. So intuitively, you can think about a1 prime and through ak prime. These are concrete. This is concrete knowledge you have about the world. This is a general rule. So what the substitution does is it specifies how the general variables here are to be grounded in the concrete things that you're dealing with. And now this final substitution grounds this part into the concrete symbols, in this case Alice, 221, and MDP. Okay, so what's the complexity of this? So each application of modus ponens produces an atomic formula, just one, not multiple ones. So that's the good news. And if you don't have any function symbols, the number of atomic formulas is the number of constant symbols to the maximum predicate arity. So in this case, if you have like 100 possible values of x, 100 possible values of y, 100 possible values of z, that would be the number of possible formulas that you might produce is 100 to the third. So that could you can imagine this being a very, very large number. So it's exponential in the arity, but if the arity is, let's say 2, then this is not too bad. It's not exponential. So that's the good news. The bad news from a complexity point of view is if there are function symbols, then actually it's infinite. Like it's not just exponential time, it's like infinite time. Because the number of possible formulas that you could produce is kind of unbounded. And when might you have something like this? Well, if you remember, one of the functions could be sum. So you could have like sum 1 and sum of 1 and sum of 1 and so on. So you can kind of essentially encode arithmetic using this first order logic. Okay, so here's what we know. So modus ponens is complete for first order logic with only horn clauses. Right? So what does completeness mean? It means that anything that's actually true, that's entailed, there exists a derivation a way of applying modus ponens to get there. But the bad news is that it's semi-decidable. This means, so first order logic, even when you restrict it to horn clauses, is semi-decidable. This means what? If f is entailed, forward inference using complete inference rules, in this case modus ponens, will eventually prove or derive f in finite time because it's complete. So eventually you'll get it. But if it's not entailed, we don't know. We don't know when to stop because it could go just keep on going on. And actually no algorithm can show this in finite time. So this is a complexity theoretic result that says it's not just exponential time, but it's actually, there's no algorithm. It's like if you're familiar with the halting problem, this is very related to that. Okay, so that's a bummer. But you know, it's not the end of the world because you can still actually just run inference and get a partial result. So you might succeed, in which you know for sure because it's sound that the f is entailed. And after a while, well, you just run out of CPU time and you stop, and then you say, I don't know. Okay, so now let's talk about resolution. So we've finished talking about first order logic with restricted to horn clauses, and we saw that modus ponens is complete. There's a small wrinkle that you can't actually compute everything that you hope for, but that's life. And now we're going to go to resolution. So remember that first order logic includes non-horn clauses. So here's an example. So this says all students know something. And the fact that this exists here, remember existential quantification is like glorified disjunction. So this is like our example of no snow or traffic. So what do we do with this? So we're going to follow the same strategy as what we did for propositional logic. We're going to convert everything into CNF, and then we're going to repeatedly apply the resolution rule. And the main thing that's going to be different is that we have to handle variables and quantifiers and use substitution and unification. But the structure is going to be the same. So the conversion to CNF is a bit messy and gross and slightly non-intuitive. I just want to present it so you know what it looks like. So here is an example of not a CNF formula. So what does this say? Just to practice, this says for all x, so if anyone who loves all animals is loved by someone. Okay. And what we want to produce is the final output is this CNF formula, which again, CNF means a conjunction of disjuncts, and each disjunct is atomic formula or atomic formula that's been negated. And here we see some functions that have emerged called Skolem functions, which I'll explain later. And that's basically it. So we have to handle variables, and we're going to have to handle somehow. And the way we do this is we remember there's no quantifiers that show up here. And by default, everything is going to be universally quantified, which means that the existential quantifiers have to go away, and the existential quantifiers get converted into these functions. Okay. All right. So part one. So there's again the 6 to 8 step procedure. We start with this input. What is the first thing we want to do? We want to remove all the symbols that shouldn't show up. Get our symbol inventory correct. So we eliminate implication. This is the same as before. So here is this thing implies this thing, and we replace that with not that the first thing or not the second thing. So now the expressions are more gross, but it's really the same rule identity that we were invoking before. It would do that for the inner expression. We push the negation inwards so it touches the atomic formulas and eliminate double negation. So this is all old news. And something new here is we're going to standardize the variables. So this step is technically not necessary. By standardizing variables, I just mean that this y and this y are actually different. It's like having two local variables and two different functions. They have nothing to do with each other. Because we're going to remove quantification later, I'm just going to make them separate. So this y gets replaced with a z. Okay, so now I have this. I'm going to replace existentially quantified variables with Scullum functions. Okay, so this requires a little bit of explanation. So I have exists z loves z of x. Okay, and this existential is on the inside here. So of this universal quantifier. So in a way, z depends on x. For every x, I might have a different z. So to capture this dependency, I can't just drop exists z. What I'm going to do is I'm going to capture the dependency by turning z into a function. And the same thing happens over here. I have exists y, and I replace this lowercase y with a big Y that depends on the variables that are universally quantified outside the scope here. Yeah?
Wasn't it loves all animals, not just one animal?
So loves all animals is in the first part. So everyone who likes all animals is loved by someone. So this is the someone part.
Oh, I'm just wondering on the exists y for animal y, how that changed from an all to an exists.
Because here I push the negation inside. Yeah. Yeah. So remember when I push negation past the for all, it becomes it exists. Okay, so now I can distribute or over and to change the order of these connectives, so that because in CNF I want a conjunction of disjuncts, not a disjunction of conjuncts. And finally, I just ditch all the universal quantifiers. Okay, so I don't expect you to follow all that in complete detail, but this is just giving you a basic idea. Okay, so now we're ready to state the resolution rule. And this should look very familiar. It's the same resolution rule as before, but now all of these things are not propositional symbols, but atomic formula. And now this is not P and not P, but P and not Q. And because these in general might be different, and I need to unify them. And then I would take the substitution returned by unification, and I'm going to apply it on the result. It's the same way we did for mode exponents. So here's an example of this. I have animal or loves, and over here I have not loves or feeds. And what do? I try to unify this loves with this not loves, and I get this substitution. So u has to replace with z of x and v with x. And that allows me to cancel these now. Now I've made them equal. And now I take the remaining parts and I apply the substitution. So this feeds u of v becomes feeds z of x and x. Okay? So there's a bit more intuition I can provide, but this does become a little bit abstract, and you just kind of have to trust that resolution is doing its job. I personally find it kind of difficult to look at intermediate stages of logical inference and really get any intuition about the individual pieces. But that's why you define the principles, prove that they're right, and then you trust that logical inference does the right thing. Okay, to summarize, we've talked about propositional logic and first-order logic. So for inference in propositional logic, you could just do model checking, which means that convert it to a CSP and solve it. In first-order logic, there's no way to enumerate all of the possible infinite models, so you can't do that. But in certain cases, you can propositionalize, and you can reduce first-order logic to propositional logic in certain cases. Or you can stick with inference rules. And if you stick with inference rules, you can use modus ponens on the horn clauses. Or you can, if you don't want to restrict to horn clauses, you can use resolution. And the only thing that's different about first-order logic here is the plus plus, which means that you have to use unification and substitution. Okay, final takeaway is, there's a lot of kind of symbol manipulation and details here, but I wanted to kind of stress the importance of logic as expressive language to represent knowledge and reason with it. And the key idea in first-order logic is the use of variables. So these are very not the same notion of variables as in CSPs. Those variables are propositional symbols, which are like the simplest thing in logic. So in logic, first-order logic, we've kind of gone up a layer in the expressive hierarchy, and variables here allow you to give compact representations to a very rich thing. So again, the kind of if you don't remember anything, just remember the takeaway that logic allows you to express very complicated and big things using kind of small formulas. Okay, so that's it. On Wednesday, we'll be giving a lecture on deep learning, and there's one, and then we have the poster session after Thanksgiving, and then the final lecture we'll give that will sum everything up. So, okay, I will see you at the poster session, and good luck on the exam.